Hello and welcome. We continue with the next module, module 4. This one covers protocols. So as we see, we keep on moving along the OSI model. Protocols reside on the layer 4. So we'll cover the TCP/IP protocols, more of the connections at the TCP and UDP level. Identify those, how they're formatted, how the header gets formatted on the Ethernet header. We'll go through every single detail that is in there. And then continue with some encryption, how VPNs and how encryption works, key management for secure connections, and some of the utilities to troubleshoot that. And this is best to see it from bottom to top. Your layer 1, remember, is your wire connection where things go there for when frames go into the bits and bytes. Your layer 2 is your data link layer where your NIC card connects. Everything gets encapsulated with a header and a trailer. This is the only part where you have a header and a trailer to create the frame. Layer 3 adds the routing information on it with your IP address, where the computers are aware of a source and destination IP addresses, right? And also has a header. Layer 4, you get a transport layer where they determine if you're using a TCP or UDP, basically how the communication is going to go. Is it a two-way communication or is it a one-way communication? And then also which port you're going to be connected on, right? We talk about TCP and UDP ports. And then layer 5, 6, and 7 are the ones where the data comes in with your payload, either to send information to someone, or when you receive information, that's where the payload comes. So all of this is basically controlled by your TCP/IP protocols, which is the ones that has all the information, the headers. Each header basically has information, or what information is encapsulated in there, right? Layer 3 encapsulation, layer 4, layer 3, and layer 2, they all do encapsulation. And that header basically has all the information of what is being in there and how to handle that. And each one has the unique information. So we'll get more into those TCP/IP protocols for the UDP, TCP, ARP, and all the rest. I had shown you in class a slide similar to this, where you get your payload, right? That comes from the layer 7, 6, and 5. When you get to your transport layer, you get a header with that information, and it becomes a segment or a datagram. Then it goes to another header that encapsulates the previous header with the payload into a packet, a layer 3, and that header has the IP information. And then a layer 2, you get another encapsulation. So everything gets encapsulated. It's put in like a package, a letter within a bin, for send it out. That bin gets loaded into a truck, and the truck gets loaded into a plane, right? So everything gets being encapsulated, and everything that it was there from before is still maintained. And just remember, notice that only layer 2 is the one that has a trailer, which is the one that actually closes that whole package into a frame. So for any communication, you start from 7, you come down all your layers. You go to your physical layer, which will be your cable, your fiber, your wireless communication, your microwave communications, any type of communication at the layer 1. And then it gets decapsulated all the way to provide that information to the application at the layer 7 on the receiver side. So when you send this information, it goes across other devices, right? So when it goes in transit, it goes to multiple devices, and they'll get inspected up to the layer that those devices are capable of. So if you go traverse through a switch or multiple switches, then switches are only capable of reading up to layer 2. So they'll decapsulate layer 2 and encapsulate again to send it to layer 1. And once it hits a router, of course, it will go up to layer 3. So this can inspect that header and say which is the source, what's your destination, and then find where to send it to so you can reach your destination. So you go through all those layers in and out, but it will get to the highest layer that the device can handle. And in our case, it will be to layer 3, which is a router, which is also layer 4 aware, so it can do the packet, the protocol that it's using. But what the router is really concerned is that source and destination. Just where is it that you want to go to and send it to the next person or the next device that will carry your information. So as we've seen before, TCP is the transport layer, layer 4, right? And here there's where you can have a connection oriented, right? TCP is a connection oriented. It will have what is called a three-step process, and we'll go through it with what is called a three-way handshake. This is pretty much you calling somewhere and you identify yourself. It's like, hello, this is such and such. And the other person can answer, say, okay, hello, and I'm also such and such. So now you start communicating with each other once you identify who's calling who and who is answering the other end. So you establish that communication. That's similar to what computers would do. And also to continue to communicate with this and maintain that communication, the TCP headers will have a sequencing numbers and checksum numbers. Imagine if you're sending a file, you can break it up in multiple pieces. So you need to put a little header with a number, so you know what's the order that you can when you receive those packages, receive them and put them in the right order to reassemble the original message, right? And also the flow control is the one that will say, I'm ready to receive more data, or I'm really overfloated right now, so just hold on. And then, or you can negotiate the flow control and say, okay, I cannot handle packages that large, I'm not that smart, so send me smaller packages. The other side will receive that. It said, okay, I can handle that. You don't want a packet, packages of this size at this moment, so I'll send you smaller packages so you can start getting all those little by little. But when I say packages, it's just packets of information, blocks of information received, that those blocks can be reduced in size so the other end can process the communication correctly. So this is that header that I'm talking about. This is the first header that is put in on your payload, right? The 5, 6, and 7 creates a payload or your data. So this header at that layer remembers TCP layer, the transport protocol. So the transport protocol, all they know is source destination ports. If you go into HTTP, you use port 80. HTTPS, you use 443. If you're doing SSH, it's port 23, and so on. So it depends on what type of information you're sending or receiving. Then you'll have here your source port, your destination port, which is part of your header, right? Your sequence number. Then you got your acknowledgement that is used to have a number that it says, okay, I receive your number, so let me acknowledge with this other number. And then there's a series of small information here with the header length and reserve that you have is more what they're called flags for the urgent, acknowledge, push, reset, send, and fin. All of those are normally set to 0, and they will be set to 1 to say, okay, this package is urgent. So that urgent bit there, because you see it's only 1 bit. If you see at the top, it's like bit 0 through 31, right? So if I receive something and I acknowledge I received it, then my acknowledge bit will be set. Push is kind of like to say, get this information. Reset said, I lost the communication, please reset the communication. The send is the same thing. That's just the send is to synchronize communication. So that's when you send the send. And the fin is to finalize, to say, I'm done. I don't have any more information. I already sent everything that I wanted to send you, or this is the last block of information for that you requested, and I'm finalizing the connection and I'm closing the connection, right? And then the sliding window side, that's for your flow control. That's the one that says, okay, how much of a window do I have to create to save your information? How many bytes of information can I send you in one chunk of data? So the sliding window will tell me, I cannot handle that. Please reduce my sliding window. And they might negotiate that between the two until they agree on a sliding window that receive information. correctly. You checksum is just a hash number to make sure that the information that you receive passes a how do I say it more? How would I say it? Like more like a quality control that when you receive it is correct. So it verifies the information is not corrupted, that everything that you got is there, and is done by a checksum. Then you got the origin pointer, you got some options, you got some padding. Padding is just in case you don't fill up all the fields and there's some space there, you have to use the whole header. So you put some padding, and then your data is there. So that whole TCP header is the first 6 lines of that header. Okay, and this is a three-way communication. Uh, it's three-way because uh, just 3 steps. So the requester sends a SYN, saying I want to sync up with you, and then the receiver sends back a SYN-ACK saying, okay, I received your SYN request, and here's my acknowledgement, and then I return back an acknowledgement saying, okay, I'm agree with you that you're ready for me, and then we can start making a communication. Once you get all that, that's when the payload and data can be sent. So the first few packets that you get is just to establish that communication. They do that handshake, and I said, okay, I'm calling you to your house, and I want to talk to Juan. I want to make sure that Juan is on the line, right? And that he's going to be listening to me, and I'm just going to be talking and talking and not knowing who's on the other side or there's anyone on the other side. So this guarantees that there's a communication between the two, and that the two applications are actually talking to each other. Remember that every packet will go up to layer 7, so the applications are aware of all of this. And this is a better way to see it, because now you see that my SYN, it has no acknowledgement because I'm starting the communication, so there's no acknowledgement. I'm just sending you a SYN. But along with that, I send you a sequence number. See the 937013558. So I send that sequence number to you. I said, I'm going to send you this, and I'm going to verify that I'm actually talking to, to the right end. So computer B will reply back with the SYN-ACK. This one says ACK-SYN, but with the SYN and acknowledgement. But also, it's going to return my number that I sent originally with a +1. See how it ends at 3558 when I sent, and then in the reply back is 3559. So it adds 1. So when I receive it, computer A received that, he goes, okay, he got my number, he got my sequence, and my knowledge comes with the right number, and then that receiver is gonna send me his own sequence number. So now he generates a sequence number. This is like a random number. So he generates a sequence number and send it to me, and along with an acknowledgement. Then I reply back with the same sequence that I just received, the one that 304.39.58669, and I reply back with 8670. I said I received that, and also with acknowledgement that I received U559. So now I know that I'm establishing a connection, and that we can start communicating with each other. But this is right before I start sending all my data. I need to start with that communication. Now, the previous TCP information is TCP. Remember, TCP, Transmission Control Protocol, um, does a two-way communication. It wants to make sure that when I send something, I'm talking to the right information, the right device, and I'm replying back. And with those sequence numbers, I know I can guarantee you received it, you're replying back to me, and I go back and forth. So that I can establish that two-way communication, right? It was three-way handshake for a two-way communication. So now we're talking to each other. Now UDP, on the other hand, is a datagram. It's a user datagram. It is unreliable. It's called connectionless protocol. The TCP is connection-oriented protocol. UDP is connectionless protocol. It doesn't require a three-way handshake. And because it doesn't have that, UDP does not guarantee the delivery of data. UDP, they has no error checking, no sequencing, no flow control, nothing. All it does is send information and just send it out. If you received it, you fine. If you did not, it's like an announcement. I send an announcement, and if everybody's listening, they'll get it, or maybe 80%, 90% of the listeners will get the message. The other percentage will just lose it, right? And as a sender, I won't send it again. I said it once and I'm done, right? That's UDP. UDP will do that. In a way, UDP is more efficient because it doesn't have all that overhead of numbers and sequencing going back and forth. And did you get it? You did not get it? Did I get the right number? Did I check the number? So that overhead, of course, creates delays and it makes the package bigger, stuff like that. UDP is more simpler, but UDP does not guarantee that. So you want that for live video, any video transmission over the internet that you send information. That's why sometimes when you're watching, I don't know, Netflix or Hulu or one of those places, and you get the images pixelized. Your audio keeps on going because the audio has a little bit of more quality of service. So the audio is make sure that it's sent with by priority. So it has you always get the audio, but the video is not so much of an importance as the audio. So if you lose a little bit here and there on the video and you get some pixelized images, it doesn't matter. As long as you keep on going and keep receiving the rest. And if there was a hiccup on the internet, you will get that blip on the screen, but then it will continue again, right? So the UDP will have a smaller header, and it will have a source port, destination port, the length, and checksum, right? Then it has the option for the IPv4, but it also is required for IPv6. IPv6, remember, is handled a little bit different, and the headers and the packets are a little bit different. So it doesn't require all that information, but it still needs to know if it's IPv4 or IPv6. Most of these headers will have a version number, so it identifies what version of IP you're using. All right, so remember that the suite is called TCP/IP. So TCP is the one that handles all that handshaking and all the communication, or if it's a connection oriented or connectionless, that's decided at the TCP. And now you got the IP protocol. With the IP protocol by itself, it's unreliable. It's connectionless. It's more like a UDP. So it relies on TCP in order to make a good, reliable communication. IP by itself, all he cares about is the source and destination. That he's the one that knows that what IP address I have and what IP address I have to go to. So remember when I compared IP addresses with your home address. So if I live at 142nd Avenue or the block 142nd on that block, and I'm going to the block 137. So I need to know those two. Where's the source? Where's my destination? Where I'm going to start from and where I'm going to go to. And then TCP will take care of the communication to come back and forth. So in case I need to return back, that information is there, right? So TCP IP, once you have all that information, once you get an IP address, that's where you can traverse more than one LAN. If you want to stay within your own LAN, with your own area network, right? Like your department, your room, on the same layer 2, you don't require that IP to jump from one computer to another. But when you need to go to another LAN, like saying from one street to another street, then you need to know that where is it that you're going to, even if it's within the same Class B or Class C. Let's say for the Miami-Dade, the 147.70. If I want to go to 147.70 10.0 network to 147.70.20 the 20.0 network, then for that TCP IP is the one that will control, have information that you're going from 10 to 20 and then back from 20 to 10. So this is the header that you'll see. Remember that layer 4 without a header, no trailer. Now layer 3, the IP protocol, it will add his own header. And this header, the difference here, look at in the middle, you have your source IP address, and it goes from 0 to 31. That's a 32-bit IP address. We're talking about an IPv4 packet, and your destination IP address. Here you have some flags. You have the header checksum to make sure that also that information it is correct. The first thing that you have there, see, is the version number. So that will show if it's IPv4 or IPv6. I need to identify a layer 3 if it's IPv4 or IPv6. TCP remains the same. Your port numbers, your sliding windows, and all that remains the same for either IPv6 or IPv4. But at the IP level, the layer 3, on that layer, then you need to then identify it with first with the version number. You have a diffserv, which is differential services. That's basically to define how important your packet is in case you need to expedite the information for videos or audio and things like that. So you have it here. The fragmented offset is there. There's some flags that you have to put in there, but like I said, the important thing is your source and destination IP. You also have your TTL. TTL is the time to live. Every packet will have what's called a time to live, which is a counter. It's just a counter. And this is an IP, right? Internet Protocol layer 3. So that's where the routers reside. So every time you traverse from one router to the next, that TTL gets decremented. So if the TTL is 100, as I traverse to one router to the next, you go to 98, 99, I mean, 99, 98, 97, 96, and it starts decremented until can be exhausted to 0. If it doesn't get to destination by the time it gets to 0, that packet gets discarded because that's the time to live. That is a way to control how far you can go within a network. If I don't want my packet to go continuously forever, jumping from router to router to router to router to router to router and never get anywhere, then that's where you need a TTL in there, because the TTL puts an expiration date on this packet that at some point, if it doesn't get to a destination, it has to expire. If I can control the TTL and make it lower, what happens is that it will traverse a certain amount of routers from my source when it's looking towards the destination. So if it's something around the world and I'm going to want to send this to, I don't know, India, but you have to traverse multiple routers to get there, I can adjust my TTL in such a way that it will never get to any router in India or Ukraine or I don't know, any country, Turkey, any country that is far from us that it might have to traverse to multiple routers. So the packet, in a way, it gets expired, so it doesn't get to a destination if it's too far. So I can control that there. But that for once, and for the other one is that the packet will never live forever. So it has a lifetime, which is the time to live. Once it traverses that many routers, if it doesn't get a destination, like I said, it would expire. So for the same layer 3 IPv6 is a little different. Of course, the IP addresses are much larger. So rather than having just 32-bit for one and 32-bit for the other one, now I need to accommodate 128-bit for one address and another 128-bit for the destination IP address. The fragmentation is not handled at this layer; is handled at a higher layer because that gets done before it gets to this packet, so you don't have fragmentation in this one. And like I said, it's different from IPv6 because of the size of the IP addresses. And ICMP, we talked about it in the previous chapter. ICMP is what ping utility uses. You can see with ping if a network is congested, if I cannot reach a destination, we can use it for troubleshooting, right? Because you can try to ping your gateway, see if you can get that router to get out of your LAN, or you can try to ping someone around you just to make sure that you're actually being seen on your network. And then you can go something further, or you can go try to ping something in China, something outside the United States, just to see how far your connection will go and how congested it is. Because ping would actually measure. Remember, the ping is like I had mentioned, like in the submarine, they will send that ping sound, wait until it hits something, and it comes back. That echo that comes back is an echo protocol. So it will tell you how far something is and how much delay is to receive that packet back to you, right? ICMPv6 is the one that is used on IPv6 networks. And the only problem with that, like I mentioned before, is trying to do a ping to an IPv6 IP address where it's 128-bit long. and then it's hexadecimal. So someone rather than saying 147.70.40.15, they have to give you the I don't know if it's a link local FE80 colon 2000 colon 1FBC colon da, 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 all the way to 128 bits. So it's a long address. Now the ARP or Address Resolution Protocol, um, it works on IPv4. Um, I had shown you an example when I was trying to identify the computer in the lab that we look at the MAC address, and for the MAC address we looked at the IP address. Well, ARP is the one that makes that association of the IP address to a MAC address, and routers at a layer 3 maintains that ARP table. They for every known computer or system on that network, the router keeps the ARP table. Oh, if it has an aging time also, whereas when a machine goes away and it doesn't come back, that will expire. If the machine is there, it will keep renewing that timer to make sure that it is alive on the ARP table. Um, so this is a combination of layer 2 and layer 3 because now, like I said, you associate your IP address with your MAC address. So it's layer 3 association with layer 2. Um, that way for troubleshooting is important because that's the way that you can see on that layer 2 where or which switch is the ones is that is seeing that layer 2. So it's the IP to MAC mapping. The address table can be two ways. Can be dynamic. Dynamic is when they register itself, right? They have also a lifetime that I mentioned that it will expire at some point. Or you can have a static ARP table where you can enter manually, which I never had to do that in my IT life, but you can add something on your ARP table. On Windows, and I think on Linux too, you can do ARP -A, and that will show you the current ARP table on your computer. Remember, your computer has an IP address, so it's layer 3 aware, so it knows layer 3 for other computers. I mean, well, your computer goes all the way to layer 7 because it has the application, but because it's layer 3, it's on layer 3, it will have all that ARP table associated with MAC addresses within your computer connection. So if you go to a command prompt and you type ARP -A, you'll get the current table for your computer. So once you issue that command, the ARP -A, you will get something like this. That will give you the internet, the IP address, the internet address, the associated physical address or the MAC address, and if it's dynamic or static. And so every time you talk to any other device, it will add it to the table. So you can see here what are your active, basically, connections that your computer is aware of. And like I said, if you keep on talking to the same device, you want to keep it on your table so you don't have to keep querying that information again where you already have it on your table. And in this, like a router, it will have an aging time too, that at some point it will just disappear. So now for IPv6, you don't have ARP. What the IPv6 has the NDP, the Neighbor Discovery Protocol. That through NDP, your computer will send multiple type of messages for the router advertisement, the router solicitation, a redirect, the NS, the network solicitation, the network advertisement, neighbor advertisement. So you get connections with everything. So the router advertisement, you go out and try to look for the router information. You can go to the router solicitation to say, hey, give me all my network information for where my link is. Remember, the link is like a LAN on IPv4. Here's it called a link. So see what's on my link. You can request a redirect. The neighbor solicitation is to say, okay, who else is around me? Who all the machines are around me that I can discover? And then because they send out neighbor advertisement to say, hey, I'm here. So they do the advertisement. So your solicitation is actually ask for that information. So you can start building your own little local table on the computer. Just the same way that IPv4 does for the ARP table on its own. So on IPv6, NDP, IPv4, ARP. So Ethernet now resides on the layer 2. So Ethernet is the standard for the data link layer. to send information across. This was it was developed by three companies, and it was called DIX, D-I-X. It was DEC, D-E-C, Intel, and Xerox. And they're the ones that came up with this standard, and it's still up to today that we still use it. And it just the way to send the information. This is where a layer two, that's where everything gets encapsulated into a frame, right? And that's what you send through the wire. That frame can be anything between 46 and 1500 bytes. The maximum, the MTU, the maximum transmission unit that you can send over a connection is MTU. The MTU is 1500. That's the maximum one. Now remember that the headers themselves occupy some space, so it's not 1500 bytes of data. The data is going to be a lot less than this because all the headers are taking some space. So once you reduce that, your data will be like in the 1400s or less than that. So the Ethernet by itself requires it would allow MTU, so the maximum transmission unit of 1500. Although there are other protocols now that they use what's called jumbo frames, because like I said, the frame is limited to 1500. So jumbo frames go beyond that, and I think the largest is 9800 and something for jumbo frames. But that's when you want to send big, huge chunks of data, because when you send them 1500 frames, your payload is small. Like I said, it will be 1300 to 1400 because of the header, the overhead. So you have to send, like if you're doing backups and information just going through, and you have to break it up into all these little, frames, so you can use a jumbo frame to send more data at a time and get information faster. It's just that every time you have to retransmit, you have to retransmit in one of these jumbo frames. So you have to be careful with that. Like I said, it's only used either for sometimes router-to-router communication, where you can increase your MTU. But even then, at the college, I have we have the frames set to 1600, just so those 1500s can fit in there and still have some overhead for the other headers for the communication. But Ethernet, it's the data standard of how information is sent across. It is a layer 2 protocol. So this is a frame with fully loaded 1500 bytes of data. So you have 1526 total. If you add 8 plus 6 plus 6 plus 2 plus 1500 plus 4, it'll be 1526. But your data can be more than 1500. Again, even some headers will use information there. So chances are, if you look at your router at home, your MTU might be set to like 1450 or something like that, because sometimes there's some overhead that is included in the headers or some other information, and it will just increase. If it's too large, it cannot be transmitted. It has to be exactly that size or less. Now, encryption protocols. Anything encrypted is called a cipher, right? A cipher is just data that is scrambled, or you have a algorithm that would actually change this data into something that cannot be read by anyone, and you will need that cipher in order to decrypt the message and read it. So just to keep everything private, make sure that there are three benchmarks for confidentiality, integrity, and availability. So you want to make sure that it's confidential, that no one else can see it. It has integrity, so you can trust it. Make sure the information that you get it is the right information, and availability to make sure that it is there and you get it to you. These are called the triad, the CIA, that you need to have. Now, there's a kind of like gray area or where encryption happens. So when you said what layer encryption happens, it depends. There's some encryption that happens at layer 2. Some others, like IPsec, is on layer 3. Layer 4 can handle other types of encryption for like SSL, TLS. But layer 5 and 6 mostly will do some of the other protocols to do encryption. But we'll go into some of that encryption, how it happens. So to encrypt the data, you need a key. Key is just a random set of characters, right? That is mixed up on your data or used to encrypt your data and to create that ciphertext. right? And they have to obey, of course, some specific rules. It's a protocol. There's some rules, so your receiver is able to decrypt your data. There's two ways to encrypt your data. Well, two categories. You can have your private key encryption and the public key encryption, or you can do the PKI that uses the private and a public key. And we'll go through some of this. So on a private key encryption, both the receiver and the sender has the key. There is a shared key. So I encrypt the document with the private key, send the document across, and when you get your private key, the same private key, and open the document with that, or decrypt it with that. It's kind of putting a lock on a document, and when you receive it, you'll have a copy of that key and you unlock it. And also you can have a public key. That the public key is kept by the a CA, a security certificate authority, that authenticates that that key is the proper key, right? So I can encrypt with with a private key. When it goes to your receiver, you can get a public key and then open it with the public keys. That's what it's called, the key there, a key pair. So my private key is different from my public key, but my public key is kept by the CA, my certificate authority, which is the one that guarantees that the key that they're giving me is the correct key to decrypt your data. Now that private key is only owned by the sender. The receiver never gets it, or the CA never gets it. That's owned by the sender. So that's like a master key that encrypts that, and then you can negotiate your public key with the CA. One of the most used protocols is IPsec. IPsec is the Internet Protocol Security. This happens at a layer 3. So IPsec is defined by rules, right? But it has certain steps that you do. You do your IPsec initialization. Or initiation, and then you have your key manager where you change your keys and set who has the my private key and the public key. Then you do your security negotiations to make sure that everything is now encrypted. Once you know for sure that your communication is fully encrypted from end to end, you initiate your data transfer. For all the information is also like I said, is a cipher, is encrypted. Once you finish, then you terminate that. There's two types: a transport mode, a tunnel mode. Transport mode is just you send the data and it gets decrypted on the other side. Tunnel mode is we actually create like a virtual tunnel between the two, and that communication is completely separate from any other communication. It's on a separate, creates like a virtual tunnel, so you two can talk to each other. Even though it's encrypted, you still create that IPsec tunnel. So the tunnel itself is encrypted, and everything is sent through it, through that pipe. It's all protected by that tunnel. Now, SSL, or Secure Socket Layer, and TLS, the Transport Layer Security, works at a layer 4. Once you see transport, this is Transport Layer Security. It works for the transport layer. That's layer 4. Its method of encryption, usually they work together. So they're either called SSL TLS or TLS SSL. It's used for a lot of web pages, communication between servers. But it does the same thing. It gets a communication. Establishes a session to get a communication, client to server, and it sends the information across, right? This will do sort of like a handshake. It creates like that's also the same three-way handshake to create that communication between the two, and establish that I'm the sender, you're the receiver, and the data is going to be encrypted, and this is how we're going to encrypt the data. Some of these certificates are different from one client to another. It's not that I'm going to take that certificate and then try to decrypt another information for another communication, because it's different. It kind of changes a little bit. So what the communication that I see with one client is different with the communication that I see with another client. So that's why it makes it so secure. Remote access protocols are just to remote into another server or a LAN or one. It depends how you're going to do it. But it uses a remote access server that you connect to the server and establish the connection to that. This is for to get the files or connect virtually to another machine, or connect through a VPN, a virtual private network. So on a virtual private network, then you, of course, your communication is all encrypted, and is done through this. As a remote access server, you might have a VPN gateway, something that is a dedicated device that is there running the specialized software. And then for the most part, actually for most of them, you want to use also a software on your client that it's a a protocol client, the VPN client, for you to encrypt your data and establish the communication. Windows has some native encryption protocols, but they're so weak that you just want to have that other software running that handles that communication at a higher level encryption. Now, FTP is a way to access files remotely, either to send or to receive. FTP is a file transfer protocol. By itself is not secure, so you need to use FTPS, FTP secure, or FTP over SSL, that it will create that encryption layer. So when you send your data or your file, it is protected by SSL TLS. You can also have secure FTP that uses SSH, the secure shell, to encrypt your data. And also, you have TFTP. TFTP is simple, similar to FTP. It doesn't have authentication or any kind of security. So FTP can be used for regular files that you want to send across. I know very common is to send firmware files or configuration files. Well, not configuration file, not the configuration itself, but you can send the firmware, something like that is not so critical that you can send across without so much security. So you can use TFTP. It's fast. The advantage of that is that FTP requires you to use a username and password, and so is a secure FTP or SPPS. You're required to use a username and password, and TFTP it does not require a username and password. You just like send who your destination is. You send a file, the other one receives it. They do some checksum to make sure that the file is correct, and guarantee that's all the whole thing with the sequence numbers and the checksums and all that to make sure the file is correct. And you get your file, but the FTP is not secure. So we do send like firmware files or something like that through the FTP with no problems. If you want to send configuration files, then we'll send it through a secure FTP that uses the SSH, and it will protect the data. So when I was talking about SSH, the secure shell, it's a software to communicate across, right? It's a command line. It's not any graphical or anything. It's purely text. That's how you connect usually to Linux servers or to consoles on any server. Most of the network devices you connect also through a command line interface. You can use Telnet or SSH. Telnet, as I mentioned before, Telnet is the one that is unsecured. That's the one that sends a letter and it replies back and says, "Oh yeah, I got that letter. Okay, let me send you the next letter. Okay, I got that letter." And it will do that for your name, for your password, everything that you send across, every screen that you send across. Any instructions that is thrown on the screen is checked every single letter. So it goes so many times across that if someone catches that, it will definitely be able to steal your data. So when you want to do on a terminal emulation, it's use SSH, and this is command line. If you want to go GUI based or graphical interface, you use remote desktop for Windows. Join me. I don't know if that's is still alive, but yeah, there's a lot of services. I log me in, or I use one that is called don't recall right now. Anyway, but there's some software that you can use. TeamViewer is one of them. VNC is a software that was actually written for Unix systems, for Linux systems, but also was ported to Windows. So you can use VNC, and the same thing. When VNC needs to send, has two applications running, one in the client as a VNC client, and then VNC server on the other end, so you can connect client to server and make a graphical user interface, a GUI, so you can see the other system. So as I said on the previous slide, yeah, Telnet is not authenticated. There's no encryption. You just want to see something, uh, uh, statistics, data that has um, logs to show, how much throughput you have or something like that. Something that is not really important. Yes, you can use Telnet. That's no problem at all. If you will see the status, if a status something is active or not active, or if I don't know if a connection is established or something like that. Yeah, sure, Telnet is okay because it just you know uh, worthless information that if somebody catches it doesn't mean anything. Now, if you want something secure, then you use a utility called for SSH, and the SSH will do the secure shell that will connect to that, and then SSH well, Telnet 2 has username and password. SSH will have a username and password, but at least those username and password that you send are encrypted, right? So you can be sure that SSH will create a secure connection. And I said all that is protected. Everything that you send through SSH is protected. So if I want to take a look at the configuration of my routers, where all the configuration is there and the passwords are there and the special configuration, special IPs or things that I don't want people to see, then I would definitely want to use SSH. Even for the switches, at the college we use SSH for everything, switches and um, routers. I think the only thing we have that use Telnet are some of the old UPSs for the battery backups that it's just because they're old devices, but the newer ones now they support SSH. Anything that is new, you'll see that it support SSH. It has to because they want to secure all that communication across. Like I said, username, passwords, and when you connect to those things, you might like a UPS, the battery backup systems. You can reboot them or turn them off, and that will shut down everything that is connected to the battery backup. So you want to make sure that even those little things are that they're not really network devices that are critical, but that they're secured correctly. This is one of those softwares, a terminal emulation software. PuTTY is very well known. I use it. Some people at work don't like it. They use other programs. But the important thing here is that they do that SSH communication. If you see on this one, they're trying to communicate with 192.168 to 100. And when you click on SSH, your TCP port changes to 22. If you use Telnet, it would change to 23. And this will establish a connection that is secure on Windows. You can use also another utilities on Mac. I don't have one on my mind right now, but they do have applications that you can use on the Macs or the Linux. Actually, the Linux is native. Linux, you install that on the console, and you install the SSH client on Linux, and it will run it straight from the console. But I'm pretty sure then that the Mac OS will have the same thing, that you go to a terminal and from there run SSH. And if you don't have it, you can install it. But it's one of those freely available applications that you can download. So for the remote access with the GUI, I mentioned the RDP, the remote desktop, is for Microsoft. That is strictly a Microsoft product, and you can remote in. You have seen me in class that I remote into my desktop, so I can show you, the routers or even anything graphical on the for when we did the DNS and DHCP, that you can see everything on the screen, and that machine is sitting somewhere else across the campus in another building, and yet I can get to my screen full color, full graphics, full everything through RDP. VNC will provide the same for other operating systems. It's just good. There's nothing wrong with that with VNC. Like I said, it was written originally for Linux, but it ported it to everything. So now computers, tablets, and smartphones can use VNC. The out-of-band management, I don't know why it's here, but out-of-band management is usually a remote management a connection to a device. Servers themselves can have an out-of-band management. So besides the server itself, you can have like a management port where you can actually, through that out-of-band, you can get to your BIOS configuration, kind of like when you boot up your computer for the first time, that you see that screen with the, I don't know, the IBM or the Intel HP screen and all that, you see all of that, just like you're sitting in front of it. But that's when you connect to the out-of-band management. It's a separate NIC card, and that separate network interface connection will have a separate IP address, and that's how you get to it. Some of the switches and routers will have the same thing, that is completely separate from the routing ports and the connections in and out for traffic. You can have that out-of-band management where you can connect to it, and you get basically kind of like the console connection. You get to that from a remote connection, and it's all through terminal emulation. We had those in some routers that are sitting in an area for an isolated network or something like that. So all that's completely isolated. I cannot get into that routing part. But if I go to the out-of-band port, which is, like I said, a separate port with a separate IP address, that all it does is have access to the management. I cannot do any routing. I cannot do anything else with that specific physical port. I mean, a physical port meaning a cable that I connect to, just like an Ethernet port on the device. I can connect to that, and I can get access to that console remotely from anywhere. All right, so now we're building up a little more. We're talking about encryption, how encryption happens, different protocols I use for encryption, remote access, how you get something remote. So the next step up is to go to a VPN. VPN is a virtual private network. Virtual private network is you create a tunnel, a virtual connection between your client and the end device. It could be a site-to-site. I can have my downtown office with my Fort Lauderdale office connected to a VPN, and they would appear like they're connected right next to each other, but they're not. They're connected to a site-to-site VPN, or the ones that we use if you want to connect to the college, which is a client-to-site. So it's your client. Any computer, it could be even your phone, can do VPN or tablet, and connect to the site or the college. It's also called the host to site because that's the host to connect to the site, or remote access, which is remote access to your environment. And also you can do a host to host VPN, which is just two devices back to back connected to each other. Now, to configure a VPN or get a VPN, it's a whole it's messy because the VPN has so many different options and so many combinations of protocols that you want to do that you really have to document that. I said, okay, my VPN is going to be like this. So when you set up your other end, you configure exactly the same way so we can talk to each other. Some of the protocols includes the L2TP, that's a layer 2 tunneling protocol. GRE was a Cisco proprietary, but now it's more like open in the wild. The generic routing encapsulation is to create GRE tunnels. OpenVPN is a VPN protocol that was also is open. It was mainly created for Linux systems, but it can be used for anything. And it's just a client to server or site to site protocol that can be used. And the IKV2, I think we'll go through this. There's also another set of protocols, but all of this can be combined with each other and create that tunnel. But ultimately, what you want is to create that encrypted tunnel between one location and another location, or one device to another device, and everything that goes across is encrypted, that only the two ends, actually the ones that have those master keys, to encrypt and decrypt that information. So since VPN creates a tunnel, that information that goes through there needs to have some information that is part of a tunnel. So you have that IP header with the IPsec header, and then you TCP or UDP information, and then your trailer, because it's all encapsulated on this IPsec. The whole your original payload is completely encapsulated into this VPN frame that it will go into an IP and into the IP packet. So it's encapsulated. It's to do an encapsulation. So you encapsulate to a layer 2 and then encapsulate to like a layer 3. I'm sorry, the other way around. Encapsulate to a layer 3 and then encapsulate to a layer 2 to send information across the wire. So these are this is a Windows page. Cisco developed GRE, and also they created the multi-point GRE. Multi-point means you can have multiple devices going to in multiple devices coming to one endpoint, right, to one destination. So you can have it all in one device, kind of like a concentrator. Um, all the things that in Cisco there's called is a dynamic multi-point VPN. Dynamic because they can be connected, disconnected at any time. So it creates tunnels from branches, locations, and it just like to communicate site to site, even within your enterprise. You can have GRE tunnels or DVM, DMVPN to send data across from one location to another within your enterprise. If I want to send my data from, I don't know, to Kendall to North, because we have a data center at North, I can definitely create a GRE tunnel between Kendall and North and then send that information through the GRE tunnel. So it doesn't have to be something that is outside your organization. This VPN networks can also be used inside your organization to guarantee the data across. One of my friends work with the Dade County uh, with the judges, and all those judges, their computers, they set up VPNs to like kind of like a multi-point GRE to send all the data across. Everything that they do is encrypted. Everything that they do, there's nothing on that communication they do out of those computers, out of the judge chambers, that is not encrypted, because they want to make sure that all the data is encrypted. So like I said, VPN tunnels and all these GRE tunnels can be used inside your organization to protect the data if you're going to take it from one location to another. Now, when you have VPNs and remote access, you have to be very, very careful, or who is allowed to use this. The VPN is not given to everybody. Um, Students don't have VPN. If you take specific classes, they might give you access to a VPN into the college, so you can access some of the servers inside the college or remote into some of the computers. I know that during the pandemic that we're completely remote, students that were taking architecture for AutoCAD, you can't ask a student to get a copy of AutoCAD and put it on their computers, because it requires a lot of memory, a lot of power, a lot of storage, a lot of heavy graphics, and the software itself is expensive. So what we did is that we created a separate uh, uh, group of users, VPN users, where we could add the students' IDs there. So those students can actually come in, and they were basically allowed only to connect to those specific machines, because you want to make sure that the VPN is only used for something very specific. So you have to make sure that even those devices, once you connect your device to my network through a VPN, that computer is actually brought into my network. It's a tunnel that extends my enterprise to that other endpoint. So any malware, any virus, anything that you have in there, it will be brought into my network, because you have a firewall that you want to protect your network. But then once you do a VPN, the VPN goes past the firewall. Well, it depends where your gateway is, but let's say it's past your firewall. So once you make that VPN connection, you're completely bypassing the firewall. So you want to make sure that, first of all, the person that has that it's the person that can be trusted and to do a specific job, not just to be snooping around or do anything that they're not supposed to do. They are protected by passwords and everything. We have now dual, they call it. It's like a dual authentication. You put your username and password, and then now you have something else that it will ring your phone, send your message, send you a PIN code, and then you have to put the PIN code. But for that, you need to have your phone with you. So it's a lot of stuff. Passwords have to be strong. They have to be changed periodically. Make sure that you don't use the same one for years. Some of the devices that it might be encrypted, or if you have any external storage, should be encrypted. But all of this is just to protect your network at the end of the day, right? You're gonna remote access to my network. I'm gonna allow you to come in here, and I want to make sure that you're not gonna do any harm by being inside with your device in here. Okay. Once you're done, please shut down your remote access. Exit out, disconnect your VPN. Don't leave it connected. If you have a smart VPN gateway for remote access, most likely if you're idle for too long, there's no communication across for, I don't know, half an hour, 45 minutes, or up to an hour, the VPN can actually time you out and kick you out of the VPN, so you have to reconnect again. I know at the college, it was funny during the pandemic because the VPN that we had, we set up a timer of 8 hours. That was your maximum session. It was 8 hours. So I will connect like at 7 in the morning, and in the afternoon it would disconnect me. After 8 hours, it would just shut me out. And it's like, okay, I guess I did my 8 hours and it's time to disconnect. I mean, sometimes I'll reconnect again so I can continue working. But we had that session that was limited to 8 hours. But I can limit that session to 2 hours, 3 hours. But it depends on what the person is going to be doing, what I expect for that person to be doing. I can limit my VPN access. But all it is to protect it. Most likely you'll have also a policies and procedures of what you can do or you cannot do when you're connected through a VPN. Now, to troubleshoot some of the connections, it's important to know a few utilities. Netstat is very important. Netstat will show you all the connections, all the TCP connections that you have on your computer. You can run just Netstat by itself. It will tell you, your computer, what source ports is using and what foreign device you're connecting to, foreign being the other end. And if you're doing HTTPS to a web page or something, you can see that, and you can see also if the connection was established or if the connection is sometimes it will say close wait, that it's just kind of like lingering there. It doesn't know to keep it or not, but it's just kind of like waiting to be closed. So it will do that. And I'll give you that information. Now, if you do netstat space /?, like on Windows, on any Windows command, /? gives you all the options that you can use. The one that I use the most is netstat -a, not minus, -a as in Apple. That will give you, all the connections that your computer is using for listening, because your computer, now that's where you can see what ports you have open in your computer. Right? And sometimes you might have a port open that you're not aware of that it's open. Like if you have, I don't know, port 80, port 443, if for some reason some application install a web server on your computer, then you can see that it's there. But remote might be enabled there. I think it's a 135 will be enabled. But they'll be listed on a column of the state, not as established, but as listening. So those ports are listening. Remember what I said, that when you're trying to connect, let's say, SSH to a device, you will try to establish a connection if that device is listening on that port. If that the port is not listening, you're not going to be able to make a connection, right? Is saying I don't have if I say port 22, if it's port 22, I don't have an SSH connection open or listening on SSH. But if I have RDP remote desktop enabled on my computer and I'm open to receive someone that can connect to my computer remotely, then that port, I think it's 3389, that 3389 that will be open for someone to remote into my computer. So that's a good thing to check to make sure that what connections are going on your computer in case something is connecting to, I don't know, so someplace in India or in Ukraine, that you want to make sure that that connection is you can close it or break that connection. Another one is traceroute, trace RT on Windows. The whole word trace route. If you're doing on Linux or Unix, Cisco routers, you put the whole word trace route. And what the trace route does, it traces the route that you're taking to a client. And let me show you the next slide. So you do trace route, you see the source is sending a packet, a UDP packet with a TTL of 1, just to see who's my next immediate router. And then he needs to reply back. And so I identify that one router. Then I send another one, a TTL of 2, which is going to expire that router. And that router replies back to me saying, oh, I'm the next router. And then I'll continue with TTL 3, 4, 5, 6, and start increasing to see how many steps I take, how many devices I come across until I get to my destination. Once I get to my destination, I get that reply back and I'm done. But what it builds is like a trail of what places you go across to get from one place to another. Kind of like if I'm taking a bus from South Miami to Orlando, and I'm taking the regular metro buses. So I might take bus 84, and I get off at I'm actually I don't know if there's an 84 route that exists that ends at Miami-Dade College, and then I talk about and take another bus that goes from Miami-Dade to FIU, and that's I don't know bus 107. So I see that I go to FIU that is on 107, and then I take another bus that takes me downtown, and then another bus that takes me from downtown to downtown Fort Lauderdale, and then at downtown Fort Lauderdale there's another bus that takes me to the local route where I'm going to I don't know Davie. I don't know Fort Lauderdale that well to say, but anyway, but I go from downtown Fort Lauderdale to Davie, so I can show that from South Miami to Davie, I took one bus to Kendall campus, one bus to FIU, one bus to downtown, another bus to downtown Fort Lauderdale, another bus to Davie. And then it actually gave me also the timing of how long that bus took. So I can see if it's taking me 2 hours to get there, I can say, well, the bus from South Miami to Miami-Dade Kendall was pretty fast, and Kendall to FIU was pretty fast, but the FIU to downtown was kind of slow. There was a lot of traffic, and then the downtown to downtown Florida was also kind of slow. It's kind of far too, right? It's a one hop, but it's a very long drive, and it takes time. But then from downtown to Davie is really quick. But what happens when I do the trace route, if that downtown to Davie takes forever, it takes me an hour and a half when it should take me like 15 minutes. So I can see through that trace route that something's happening between that last leg of the traffic between Fort Lauderdale and Davie, where there's a big delay that it shouldn't be there, right? And then now I have to investigate why it's taking that long there, and then concentrate on that. And trace route is when it tells me that. So trace route will route me to all the different routers, and then when I see that timing, how long it took from one to the next, then I can say, oh my God, there's something here that is causing either the problem, either because it's far, the connection is slow, or it's congested, or something is in the middle. But traceroute helps me to do something like that. So I'll do a ping. The ping will just say, hey, yeah, I'm there. I can get to the end. I can get from South Miami to Davie, and it comes back. The ping goes there and back, there and back, there and back, no problems. But when I do the trace route, it tells me now step by step that ping actually took to get there and come back. And it comes back the same route. Fort Lauderdale, downtown Miami, downtown FIU, Miami-Dade to South Miami. So trace route, really important. Now, TCP dump is a free command line package sniffer. It's native from Linux and other Unix-like. Is not native on Windows. You can definitely get an application, and you will get it. As a matter of fact, the assignment number 2 is going to be based on a TCP dump. We're going to run a packet sniffer, and you're going to analyze some of that. The packet sniffer is the one that captures everything that goes through that wire. Everything that goes through the wire, and you'll see every header for the layer 2 header, the layer 3 headers, the layer 4, everything that is there, any information, all those flags, you're going to see them on a TCP dump. Wireshark is one of the applications that I'll recommend to use for that assignment. But Wireshark, it gives you like a graphical interface. You got a top pane with some information at the bottom. That it will give you all that information. So all those little flags, everything, the reset, the send, the sequence numbers, and all that, you can trace it, because now you see all the packet going in and coming back. Everything that goes through that wire on your computer, it will take it. That's what's called a packet sniffer, because it sniffs everything. But on Linux world, it's called a TCP dump. It gets all that TCP protocol, and it dumps all that information into a file that you can see, or you can throw into the screen to see it. It just scrolls really, really fast. So on TCP dump, what you can do on the command line is set up some filters, some switches they can do, like dash this, dash that, and then you start filtering for different things, different interfaces, or specific packets that you want to filter, so it will show only that. Or you can get the whole raw data, but raw data is a lot of information. Even in 1 minute of data, it's a lot. When we're in class, I'm going to show you some packet sniffing with Wireshark, so you can see what I'm talking about. Now, duplicate MAC addresses can happen. That two devices with the same MAC address. Um, they can be done by software. Someone can do what's called spoofing, which is to impersonate another MAC address. Remember with DHCP that I can actually do a DHCP reservation based on the MAC address of one computer. If I know that I don't know, that I work at the college and my machine gets a specific IP address, that IP address that I get, it's allowed to get into some important systems in the college. Then someone can impersonate my MAC address, get that IP address, and then that IP address has access to all those systems. For example, to log in to the boarded routers, the routers that connect to Miami-Dade to the internet, they can only be managed from some of the computers in my area, including my computer. If you go from anywhere in the college, even if it's my laptop, I can't connect. I'll have to basically remote into my machine at work and my desk, and from there I can remote into the border routers. If someone spoofs that MAC address and gets that my IP address, they should be able to open a session. They don't have the password, but they're already one foot inside to break into something. So it happens. Now, another way that you can have a duplicate MAC addresses is through virtual devices, virtual machines. Most of this, they generate their own MAC addresses, but the problem is that if it's the same software, it will use the same algorithm or the same base to generate MAC addresses. So chances are you can have two systems that are completely separate but running the same software, and when they generate MAC addresses, they generate the same one. And I've seen that in the college, that actually what they recommend when you start one of those systems is to change something on one of those MAC addresses, one of the numbers. All you need to do is to change a few of the MAC address numbers, so everything gets generated now based on that one, and it's going to be totally different from another system 2 and system 3. But at the college, some of the server people forget to do that, and you got 3-4 systems that based on the same base MAC address, and then you start getting some duplicate MAC addresses, and routers will complain about that because routers trying to build that ARP table, the IP to MAC address table, and when they see that I got the same MAC address with multiple IP addresses, right? Because MAC address that's one is duplicate, not a duplicate IP. So they get same MAC address with different IP addresses. So the router is like, oh, okay, so I got traffic, but it's coming from this MAC address, but which IP is the one associated with that MAC address? Because now I got multiple ones. So it creates problems. I like this slide. They continue saying solving problems. Well, you're not going to solve problems with traceroute and ping. You can troubleshoot the problem, but not solve it. But yeah, traceroute and pings are two good utilities that you can use. The first things that I would use on troubleshoot anything is that with ping, just to troubleshoot my network card itself and the trace route to see how the communication goes. So those are two utilities that they're really handy to use and be familiar with and have it on your mind. So anytime there's a problem, then start with this. I remember when I started in networking, they used to make fun of me because I went to a training, and every time there was something, goes, well, you ping it. And then when you ping it, oh, just trace route to it. And they say, yeah, you like to ping everything. It's like, yeah, because you ping first, and then you see if there's a connectivity. If there's a connectivity, then I can do trace route. But trace route tell me more than just a ping. Ping just says, yeah, I'm there and coming back, but how is it that I'm getting there? So that's when I need the trace route. But a combination of the two is where it can help you get some information to see what's going on and make an assumption of what the problem is. Okay, so this is the end of the chapter. We will continue more. I mean, the networking, you'll see it on the other chapters. It will come back to protocols. It'll come back to encryption. It'll come back to this. The author has removed some things that I really like from the encryption part. On the previous books, he will get more heavy into the encryption. I hope that in some of the future chapters it will go back into it so it can explain and get more, because the more you know of the protocols, the more you know of your networks, how they work and how they behave, it will help you to design something good or troubleshoot something that is very complicated. So anyway, thank you for listening, and I'll be here for the next one.